In this lab exercise, we are going to build a finite state machine in VHDL, and we're going to use a combination of structural design and also concurrent signal assignments as the modeling approach. So what we're going to build is a 4-bit binary up-down counter. So this is a counter that, if you think about the next state logic for this, you're going to have 4 bits as the current state, and then you're going to have an input which dictates the direction. So you're already at a point where the size of this finite state machine has 5 inputs, and it would be extremely difficult to create the next state logic using a classical design approach. In other words, it's very difficult to do a 5-input K-map. So we've already this is of a size that is that warrants the modern digital design flow. So what we're going to do is we're going to design this state machine using a component that is going to be provided, so a D flip-flop, and we're going to add that to our file, so we'll get experience with understanding how to add a pre-existing design file. And then we will instantiate that, and we will implement the 3 parts of the finite state machine, being the state memory, next state logic, and output logic, and we will synthesize it on a DE0 CV board. And what's neat about this is that we're actually going to reuse our 7-segment display decoder and also our prime number detector from lab 6.1. And so what we can do is we can actually use the 4-bit output from the finite state machine to drive those 2 logic blocks. And so we'll be able to get everything working on our breadboard like we have in the past, namely the 7-segment display, but we'll also allow it to count by itself. So we'll bring a clock into the finite state machine and we'll let this thing run on its own, and we'll hands-free see all the characters cycle through, and then when you have a prime number, the buzzer will go off and an LED will assert. Okay, so what you're going to need for this, you're going to need your breadboard and wires, the DE0CV FPGA board and USB cable, and we're going to use the analog discovery to bring in the clock. So we'll use just the arbitrary waveform generator. Then you need on your breadboard your 7-segment display circuit from your prior lab, LED driver from prior labs, and your buzzer circuit from prior labs. And then we're going to connect these together with 10 female jumper wires. Okay, the deliverables are pretty simple. You're just going to do one video that shows the entire thing working and then provide your top.vhd. Okay, let us begin implementing the finite state machine. So the first step is we have to design the logic for it. Okay, so let's take a look at the block diagram for this. So this is how everything is going to work in this exercise. So if you look at this block over here, this is going to be the DE0 CV, and on the FPGA what you're going to have is you're going to have a finite state machine, which I draw as this dotted box. You're also going to have a 7-segment decoder and a prime number detector. Both of these are 4 input, and these are from prior labs, so we're going to use design reuse for those. What we're going to do is this finite state machine will have an output which is a 4-bit vector. It's going to be a count, okay, a 4-bit binary counter, and it comes out as 4 individual bits, but it's just a simple binary counter. In order for this finite state machine to run, it needs a clock, which we'll bring into the FPGA over here, and it needs a reset, which we'll bring in over here, and then it's going to have one input control signal called up, and that'll dictate whether it counts up, if up is a 1, or if it counts down, if up is a 0. The clock is going to come from the analog discovery channel 1 of the arbitrary waveform generator, but we need a way to get it into the FPGA. So what we'll do is we'll use the wires or the leads from the analog discovery, and we'll connect it to pin 1 of this GPIO _1 header on the DE0 CV board, and this is the one that we've already used to drive the breadboard 7-segment display, but we have this extra pin right here. So what we'll do is we'll bring over the clock onto this pin 1, and then it'll come into the FPGA on pin H16, and then we have to connect the grounds together of the analog discovery to the CEV or the DE0 CV board. So what we'll do is we'll bring the ground lead and we'll put it into pin 12, which is the gap in between these signal leads over here. So we do that, we bring the clock in. The reset is actually going to come from key 4, which is a push button switch on the FPGA board. And this is a nice switch because when you press it, it goes to a 0. And so that means that the D flip-flop has an active low reset, and so this is perfect. When I press this, it's going to reset the finite state machine. The up input will come from the slider switch on the FPGA board, SW0. Okay, so notice that we're not going to use any of the slider switches like we did in the past. We're just going to use one this time. Okay, so now once you give it a clock and you start running, what's going to happen is this counter is going to be generated. Well, what we'll do is we'll bring it out and drive it to the red LEDs on the FPGA board so we can see that it's counting in a binary fashion. And then what we'll do is we'll bring it over and drive it into the 7-segment decoder block that we had, and it will produce 7 outputs, and we will again jumper those over to our breadboard and drive the character display on the breadboard itself. And then we'll also have a prime number detector, and we'll take that 4-bit counter and drive as the input into that guy. And then it's going to produce a prime output, and we'll jumper that over, and it'll drive the LED and the buzzer on our breadboard. So what will happen is once you hit go on this, you'll see the character display run through, and every time it hits a prime number, it'll beep and assert this. Okay, so that's the block diagram of what we're going to do in all the pin assignments. This is what it's going to look like when you wire it up. So you'll notice, here's the analog discovery, here's the arbitrary waveform generator coming into here. Here's all the jumper wires that jumper the 7 signals that drive the character display. Here's prime, it comes over and comes down to this little LED in your LED driver. And then, of course, I jumper it up to the buzzer, which is sitting there. And we need to bring power to the breadboard, and we're going to bring it from the FPGA board, not from the analog discovery. So that's important. We're only going to use the arbitrary waveform generator from the analog discovery. So we need to bring that over there. And when we do that, everybody has the same ground. Okay, so the analog discovery's ground comes over and connects to the FPGA board. The FPGA board ground connects to the breadboard. So all of these can communicate with the same logic levels. Okay, over here, LEDR, that's going to show the binary count of our finite state machine. Switch 0 will be our up signal, and then the reset is this guy right here, this smaller push button. Okay, so we are ready to go. So the first thing that you should do is breadboard the finite state machine system. So to do this, really all you're doing is, you should have these circuits on your breadboard. Really all you're doing is just connecting the arbitrary waveform generator and ground to these pins, and then you're going to jumper these pins over here. So you should be able to do it with 12 female jumper wires, and that's really it. All this other stuff is already on your breadboard. So put all that together. Don't turn anything on yet, though. You can plug in the USB cables, but let's leave it off for a second, and we'll get the Cordis project working first, and then we'll turn it on. Okay, now let's get to the design. So this is going to be, everything's going to be designed in VHDL, but to design this finite state machine, we need to know what its behavior is. So I provide you a state transition table. So again, with a counter, counters traverse their states linearly, whether they're going forward or backwards, but you tend to not need a state diagram. So what we can do is we can jump right to the state table. And another thing that we can do with a counter is we want to use what's called state encoded outputs. What that means is that we want to encode the states such that the current state code itself is the output that we want. And in a counter, this works very well, because if we assign the state codes in a binary fashion, then what will happen is I traverse through the 16 possible states. The state code is the 4-bit representation in binary of that state. And so what happens is the current state can be the output itself. And that's reflected if you come through and you list the current state codes out. You'll notice that the output always has the same value. And then not only is that nice in terms of coding this up, the outputs simply become the current state. And so it's just a simple signal assignment. And we'll see that. But we have to actually come up with the table of ones and zeros that we want for the desired behavior of this. So what I would like you to do is I want you to name your current state variable q_cur, and we're going to just treat it right from the start as a 4-bit vector. So I go ahead and put it in here as qcur 3 down to 0, and this is how we're going to implement it in VHDL. I want you to call your next state variable qnext and have it be a 4-bit vector, and then I want count to be your output and have it be a 4-bit vector. And so what you'll see is, as I break these out into their scalar forms, you're going to assign a binary state code to all these states, and I just call them S0, S1. So S0 is going to have a current state code of 0, 0, 0, 0. S1 is going to be 0, 0, 0, 1. But for each state, there's 2 possible input choices. So up could be 0 or 1. And the reason that's important is because that dictates what the next state's going to be. So if up is a 1 in this row right here, what you'll see is that your next state was S1, and its state code was 0001. But if up was a 0 and you were in state 0, you're going to go to 15, and that code is 1111. So what you need to do is fill this entire table out. And the reason this is really important to do, or actually really advantageous to do, is because when we go to code up the logic for the next state, we are going to be able to do an assignment to QNext as a vector. So what we're going to do is we're going to look at current state and in, and we'll use a conditional signal assignment, and we'll be able to assign a 4-bit vector to this. And when we do that, we are essentially creating 4 separate combinational logic circuits with 1 vector assignment. So it becomes very nice. Okay, so go ahead and fill that in. And then the next thing we need to do is let's fire up a Quartus project. Now what we want to do is we want to use our 7-segment decoder and our prime number detector from lab 6.1 since they're already done. So why don't you go, what we want to do is let's open that project and then we'll copy it. You need to go File, Open Project, and then you browse to Logic Lab, and there's our guy. And then I named it Descriptive, so it's going to take just a second to load up. Okay, so now it's loaded. And what I'm going to do first is I'm going to come into the project menu and I'm going to say Copy Project. Okay, so now at this point, what I want to do is I want to name this something descriptive and create a folder. So I'm going to call this 07.3, and I'll call it 4-bit count, abbreviated CNT FSM. Okay, so that's going to be the destination directory, and then I'll name my project the exact same thing, and I'll open it once I copy it. And it's going to say, you sure you want to create this folder? And I say, absolutely, I want to create that. I want everything in a folder. Okay, so here we are. We now have this project that's starting up, and everything's great, and we're ready to start. Okay, so the first thing that we want to do is let's add the D flip-flop to this design. Okay, so there's a D flip-flop that's provided to you on a website, and you want to download that D flip-flop, and then what you want to do is you want to place it into this working directory. Okay, so what I'm going to do is I have my, let's see here, let me bring up, here is my folders that in my Logic Lab folders, and I go into the 7.3 folder, and notice I have my top.vhd in here. So I want to put this D flip-flop in there. So I go ahead and I download it from a website or from the website, and then I'm going to paste it right into here. Okay, so there's my D flip-flop. So now I have this D flip-flop in my project directory, and I want to add it in Quartus. So to do that, what I do is I come into here and I say project, add, remove files in project, and so then this window will come up, and what you want to do is you want to browse by clicking on this little button right here, and I'm going to click D flip-flop. Notice it sees my top. I'm going to click on that, and it comes into your file list. Now we want to move it down because the list here gives a priority, and we always want the top to be on top of the list. So I'm going to highlight it and move it down, and that means that whatever the top file is, that's the highest level in the hierarchy, which we always call top. So we just want to, this just tells it that D flip-flop is going to be, you know, below top. Okay, so I go ahead and say okay, and now everything's great. I have added that to my file, and if I wanted to see it, what I could do is I could come over into my hierarchy and say files, and I could double click on D flip-flop, and I could see what it looks like. So I see that it's D flip-flop, it's got clock, reset, DQQN, and it's got some logic in here that we haven't covered yet, and it is a rising edge triggered D flip-flop with an asynchronous low reset. Okay, all right, whatever. Okay, so now we're ready to start modifying our top. So go ahead and double click on that, and the first thing that we want to do is we want to update the entity, okay, because we have some new ports that we're going to bring in. First of all, we are going to have a clock input, and I'm going to go ahead and just go, it's going to be in, type bit, and I'll do these on separate lines. The other input we're going to have is going to be reset, and I'm going to have that right here. Okay, and it's also an input. And then the third new input is going to be called clock. No, not clock, up. Okay, so those are my three new. And what I want to do now is I want to delete switch because I'm not using that. Even though that up is going to come in on a switch, it's not called switch. So we get rid of SW. Now we want LEDR as our 4-bit vector. We want prime as a scalar that's going to be the output of the prime number detector. And we want our 7-segment display. Okay. Notice one thing. We don't have count. Okay, the output of our finite state machine is going to be an internal signal. Now we will assign it to LEDR, but for now we're just going to create it as an internal signal. Okay, so we have our entity updated at this point, and so this is great. So now what I want to do is I'm going to start using my D flip-flop for the state memory of of the state memory of the finite state machine. So I know that I'm going to have to do a declaration. Okay, so a declaration is before you start modeling behavior after the begin statement, you have to kind of tell the system what's going on. Okay, so let's do the following. I have to come in here and I am going to declare the D flip-flop as a component. Okay, and so the way that I do that is, notice I'm before the begin statement. I'm going to say component, and then I'm going to do D flip-flop, and then I come in and I do the ports. And what I can do is I can actually just double click on D flip-flop and get its port map right here. So I'll go ahead and just grab that right there, just so I don't make any mistakes. And so I'll go ahead and paste that in there, and there is my component declaration, and I just do an end component. And now what this means is that I can actually start using this. So this is nice. I'm gonna declare it that I will be using it later, and we're done with that. Okay. Then the next thing we need to do is we need to add some signals. So if you think about internal to the finite state machine, we're going to need signals for our current state, our next state, our output, and then these signals are going to be connected to the D flip-flop for the state memory. But the state memory also has a QN, so we should create a vector so we can wire it up to QN, even though we may not use it, but we never leave anything dangling. So we need to declare some signals, and so you do that by typing signal. This is declaration, so it means it's before the begin. So I'm going to do a signal, and let's do a Q underscore next, and let's go Q underscore cur and Q not underscore cur. And those are going to be all 4-bit vectors. So I'm going to give it the type bit vector 3 down to 0. And now that those 3 4-bit vectors can be used by my logic. And then let's do another one that is going to be called count, and it's also going to be a 4-bit vector. And this will be this is going to be the output of our logic here, of our finite state machine. Okay, so all our declarations are complete, and what I want to do now is I want to start modeling our finite state machine. So the first thing I do is when I model behavior, it's after the begin statement. So I'm going to come in here, I'm going to put a little comment right here that kind of separates the finite state machine parts, and there's going to be 3 components to this. One is going to be state memory, so this is going to be the finite state machine, and I'll come down here and this will be the state memory, and I'm going to instantiate the D flip-flops. Okay, so the first thing I want to do is I want to put down all these D flip-flops. Well, this is a 4-bit counter, and which means it has 16 states, and we're going to do state encoded outputs, and that means that I need 4 D flip-flops. So what I'm going to do is I'm going to pop in 4 instantiations of these D flip-flops, and when I do this, I need to wire them up accordingly. So I'm going to call this first D flip-flop DFF0. I call this D flip-flop name of this component up here that I declared, and then I say port map. And look at how I connect up to it though. I have the clock, which is going to come from the outside world, and it goes to all 4 of them. Reset comes from the outside world, and it goes to all 4 of them. And then for the D input, I'm going to have Q next, and then I'm going to pick scalar 0 or bit 0, 1, 2, 3 for that. And that associates those particular bits of next state logic with that D flip-flop. That means if I'm going to drive the 0th bit of next state logic into this flip-flop, I need the 0th bit of my Q cur to be on the Q output, and my Q not bit 0 to be on the Q not output. And so I pop in all these, and you can see how I counted them 0, 1, 2, 3. What I've essentially done at this point is I've put in 4 D flip-flops and wired them up to the state variables, and I've implemented the state memory. Okay, Okay, so now let's do the next state logic. And it is going to be, we are going to assign to Q next. That is what the next state logic is. Now the next state logic here is pretty easy to model with a conditional signal assignment. So if I go over, I'm going to go grab my code. I gave you a little bit in the handout on how to do it, but I'll just paste this here and so you can kind of see how to get started. What I do is I assign to Q next, and I'm going to say it gets 0001 when Q cur is 0000 and up is equal to 1. And then it gets 0010 when Q cur is equal to 0001 and up is equal to 1. So you might ask yourself, where am I getting these values from? Well, these values are from the table that you created in the first step. So these are going to come from this table. So if you look at this thing, you know, when current state Q cur is equal to 0000 and up is equal to a 1, next state is 0001. So this is pretty neat because I'm able to look at 5 input codes, 5 input bits, and make one vector assignment to Q next. And it's very powerful because a conditional signal assignment, I can use this Boolean AND operator and I can join these together. So if you have 5 input bits, that means you're going to potentially have 32 possible input conditions, and that's fine. I listed them all out like this. I put all the ups in one section, and then I listed all the downs down there. But this now constitutes your next state logic. Okay. So then the last thing you want to do is you want to do your output logic. And this is really great because all we are going to do, since we use state encoded outputs, is say count gets assigned Q cur. And those are both 4-bit vectors, and so that's the beauty of state encoded outputs. Okay, so it's like, okay, this is fantastic. I've just modeled my entire finite state machine. Okay, so now let's do the next thing. Let's think about the next logic we want here. Well, here's the logic from lab 6.1. I had assigned LEDR the switch values before. Well, now we don't even have the switch values. We're just going to do count. So that now sent all of the bits, all of the outputs of the finite state machine to LEDR. And now here comes our prime number detector. So remember that we used a selected signal assignment for the prime number detector, and its input was SW. And then it looked at SW and said it's a prime number for these particular codes. Well, we don't have SW anymore. It's going to look at count. So I need to update it. And then the same thing for the 7-segment decoder. For 7-segment, I don't want SW anymore. I want count. So I want to look at count as the input variable. And so I need to update all 16 of these. And at this point, we are ready. Okay, so what we want to do after you update these is we want to do a compile and make sure that we don't have any syntax errors, and then that will map in the new ports into Pin Planner, and then once we succeed, we'll go back into Pin Planner and we'll actually assign the pins. So I go ahead and save that, and I'm going to come over here and I'm going to double click on Compile Design, and we'll let that run for a few seconds here. Okay, so it's completed now, and I didn't have any syntax errors, but what that did is it allowed me to import the information into Pin Planner about my new ports. So I go ahead and fire up Pin Planner, and one of the things I need to look at are the new ports there. So let me scroll down to the bottom here, and one of the things I notice is that my new inputs are there. You know, I see clock, I see reset, and I see up, but I also see SW. And I need to get rid of these because these were from a prior project. So what I'm going to do is I'm going to highlight them all, right click, and say, not right click, I'm going to just highlight them and hit delete on my keyboard. And it's going to say you want to delete switch 3, yes, switch 2, yes, switch 1, yes, switch 0, yes. So you manually tell it all these things. But we do have a couple things we need to add in here. We need to actually add the locations for these 3 new inputs. And we also need to we should put their logic level. So the clock, if you recall from the block diagram, came in on pin H16. The reset came in on pin P22, and up came in on pin U13. Now, up was let's see here. So here's my IO standard. Up was an internal signal on the DE0 CV board, so we can leave its default as 2.5 because they all talk to each other using 2.5. Reset was also 2.5. So we don't need to do anything with that. But the clock, we're going to bring that in from the arbitrary waveform generator. And we'll use our standard 3.3 volt logic on that. So we'll go ahead and do 3.3 volt CMOS. Okay. All right. So everything looks good in there. I've got assignments on everything. I'll go ahead and file close. And at this point, we need to run compile again and allow this thing to synthesize for the new pin assignment. So I'm going to go ahead and compile design, and we'll let this run for a minute. Okay, so it succeeded. So at this moment in time, what we want to do is bring up the programmer. But before I do that, I'm going to go over and I'm going to turn on the device. So I go ahead and double click on Open Programmer. And it goes out and finds it. It's on, so it finds it, and it has USB Blaster on there. Okay, so what I'm going to do at this point is I'll go ahead, my power's on, and I'll go ahead and download this. Okay, so it's going to take a second to download. And when it does, we'll see a couple things. Number one, you'll notice that it's not doing anything, okay? And that's because it doesn't have a clock. Well, in reality, it is doing something. It just hasn't received that first clock edge. So you do see 0 on here, okay? And that's good because it did verify that we have power on our breadboard. So it could be running. We don't know. I mean, if I hit reset, you really can't see anything because it's going to put it back to 0 anyway. So at this point, let's fire up the analog discovery, and let's see if we can get the wave gen going. Okay, I had to plug in my analog discovery, and now I've got waveforms, and it fired up and it recognized it. And so I'm going to do a wave gen. Okay, and all I want to do is create a square wave on here, and I do not want to provide power. Okay, so remember the FPGA board is providing power to the breadboard, so we don't want to use any other tool. So what I'm going to do here is let's go ahead and set up our traditional square wave, and let's run it at 4 Hertz, so that'll be pretty quick, and then let's go 1.7 amplitude, 1.7 offset, and that gives us a nice swing between 0 and 3.4 volts, and we'll go ahead and run it. And now we want to inspect whether this is working. So check it out. Look at what is happening here. We have the clock is coming in. We have the 4-bit outputs, the 4-bit counter value of the finite state machine displayed on the red LEDs. We have the hex symbol of that displayed over here, and you can actually see it counting now. So 0, 1, 2, 3, all the way up to F and rolls over. Notice also that every prime number asserts over here, and I can turn on my buzzer if I wanted to do that too. So every time a prime number comes by, the thing beeps. This is fantastic. So let's check 2 other things. Can I take my slider switch and make it count down? And the answer is yes. Now it's going backwards. So this finite state machine is responding to what we're doing. And then the last thing to check is, first thing, let's turn that buzzer off. I'm going to hit reset on this and see if it goes to 0. So I hit that button. Look at that. It went to 0. If I hit it and hold it, it goes to 0. Then it starts counting. So we have done it. And this is a pretty major accomplishment. If you take a step back and think about where we're at, we have covered 7 chapters in this learning activity, okay? And you think about chapter 1 was analog versus digital. So we kind of understand it's like, you know, the analog versus digital thing happening here is, you know, we're sending information and over here across an LED and it's turning on or off. So that kind of represents the analog versus digital behavior. Number systems was chapter 2. Look at the number system thing that's going on right here. So number systems, we have binary and we have its equivalent hex value over here, so you kind of get a glimpse into number systems by looking at this. Chapter 3 was interfacing. Well, there is no better example of interfacing. We have a ground shared across these 3, and we're sending a 3.3 volt logic level back and forth between these systems, and it's being interpreted. Chapter 4 was combinational logic. Well, you think about combinational logic, we have a prime number detector in here, which is a combinational logic circuit that looks at 4 inputs and produces a single output. Chapter 5 was VHDL. We just did a whole ton of VHDL on this FPGA. Chapter 6 was MSI logic. That was a 7-segment decoder. The decoder is exactly what MSI logic is. And then chapter 7, we started looking at sequential logic, and we have built a state machine. So we built a finite state machine that implemented a counter that is synchronous to a clock. So this lab represents coming a long way. It represents working through all 7 chapters of the Introduction to Digital Logic, and this is awesome. I mean, if you can get this working, you should feel really good about yourself, because this is a huge accomplishment, and a whole lot has happened to get to this point. Okay, so we are done with that exercise, but before we leave, we should ask ourselves just a couple questions here. So, after doing this, could you look at the concept check and answer these questions? Could you add a pre-existing VHDL file to a Quartus project to be used as a component? So we did that with the D flip-flop. Very important as you get larger and larger designs, because you're going to be doing a lot of design reuse, and it's not just copying projects, it's creating VHDL files outside of Quartus and bringing them in. Could you implement the state memory of a finite state machine structurally, meaning instantiated as components, by instantiating the individual D flip-flops? And can you implement the next state logic and output logic of a finite state machine using continuous signal assignments? And that was the conditional signal assignment, and then just the count gets Q-cur assignments. So if you have it running, you did all 3 of these things, and you should feel pretty good about yourself. So we are done with this exercise.